Question 6. How does the pH of the solution on the left? The Kb value of NH3 is 1.8 times 10 to the negative 5. And then they just give us different options. Both of these solutions are equally acidic. Solution on the right is neutral. Solution on the right is more basic. Both of these solutions are equally basic, or the solution on the right is acidic relative to the solution on the left. Okay, so this is a multi-step question because we are given two different solutions. One of them is a strong base, which is sodium hydroxide, and one of them is a weak base, which is just ammonium. So for step 1, let's just find the pH of the strong base first. The pH of NaOH. So if we were to write down the dissociation of NaOH into its ions, it completely dissociates to Na plus and OH minus, and everything is at a 1-to-1 ratio. So since the concentration of NaOH is given, it's equal to 0.0001 molar. This is the same concentration of our hydroxide ion, which is OH minus. So it helps to know the concentration of your OH minus ion because it will help us find the concentration of H3O plus, which helps us find the concentration of pH. So let's recall that Kw is equal to the concentration of H3O plus times the concentration of OH minus. So the value of Kw is the same. It is just 1.0 times 10 to the negative 14. And we are looking for the concentration of H3O plus. And we know the concentration of hydroxide, which is 0.0001 moles per liter. So then we can just solve for the concentration of H3O plus, which is just 1 times 10 to the negative 10. Okay, so now over here we can find the pH, which is equal to the negative log of H3O plus and in the previous step we found it was 1 times 10 to the negative 10. So its pH is just 10. And then this is for the NaOH solution, which is on the left. So now step 2 is just to find the pH of our weak acid NH3. Or weak base, sorry. Weak base. So weak bases only partially dissociate into their ions. So I'm going to show its dissociation equation. So in water, it dissociates to OH minus. plus NH4 plus. So we can construct an ice table to help us solve for the concentration of OH minus. So we know the initial concentration of NH3 is 2.5, and the initial concentrations of both of our products is just 0. The change is plus X for the reactant. Oh, sorry. It's minus X for the reactant and plus X for both of our products. And then at equilibrium, the concentration of NH3 is 2.5 minus X, and the concentrations of our products is just equal to X. So first we can write the Kb expression, which is just equal to the concentration of NH4 plus times the concentration of OH minus divided by the concentration of NH3. They gave us the Kb value, which is 1.8 times 10 to the negative 5. And then if we sub in what we found in our ice tables, we get x squared divided by 2.5 minus x. So from here, we can simplify this equation to get it in a quadratic formula form. So putting everything on the same line, we get x squared plus 1.8 times 10 to the negative 5x minus 4.5 times 10 to the negative 5 is equal to 0. So at this point, since we have a quadratic formula, we can plug it into the quadratic equation, or you can just use an online calculator to solve for your x value. And we always want to get the positive value because there's no such thing as like a negative concentration. So the positive x value is 6.7 times 10 to the negative 3. Do this in a different color. Okay, so now that we have our x value, this is also the same as the concentration of our OH minus ion. So again, let's recall that Kw is equal to the concentration of H3O plus times the concentration of OH minus. Kw is equal to 1.0 times 10 to the negative 4. And then we just sub in 6.7 times 10 to the negative 3 as our concentration of OH. And we get a concentration of H3O plus that's equal to 1.49 times 10 to the negative 12. So finally, we can sub this value in our pH equation. And we get a final pH of 11.83. And this is for NH3. Okay, so now let's look at both of our pHs. And we can see that solution on the right is more basic. So that tells us that it is option C. The solution on the right is basic relative to the solution on the left. Okay, so it's a very long question. Everything somehow fit on one page. The junior tutor said to compare the pH of the solution, we need to first calculate for the pH of the solution. Let's start with the easier of the two, NaOH. Since sodium hydroxide is a strong base, it will completely dissociate into sodium plus and OH minus. Then we can use the self-ionization of water to get the concentration of H3O plus ions. So Kw is equal to the concentration of H3O plus times the concentration of OH minus. So they got 1 times 10 to the negative 10, and they got a pH of 10. Then we need to calculate for the pH of NH3. To do this, we need to calculate for the concentration of H3O plus, and we need to use the ICE table. Okay, so they did the same work. They plugged in their Kb value as 1.8 times 10 to the negative 5 and got a quadratic equation, x squared plus 1.8 times 10 to the negative 5. There should be an x here, minus 4.5 times 10 to the negative 5. Okay, so they show their work plugging everything into a quadratic formula, and you pick the positive root. Since we want to obtain the concentration of OH minus, which is 6.7 times 10 to the negative 3. And then they subbed that in to the Kw expression and got a concentration of 1.49 times 10 to the negative 12 for H3O plus, and then they plugged it into the pH equation to get 11.826. So the solution of NH3 is relatively more basic, therefore the answer is C. Yep, so this solution is correct.